Hi folks, my name is Rod Price and I'm making this video here to help introduce you to the concept of magnetic fields. So I'm going to start this with a quick little demonstration here. What I've got is a plexiglass box here that's filled with an oil, and within it are iron filings that are very, very, very fine. So I'm going to kind of shake it up and get them kind of uniformly distributed, and hopefully this comes through on the video pretty well. They're pretty much uniformly distributed and there's no particular pattern. Okay, now I'm going to take a magnet and just put it on the bottom here like so. And the important thing is to pay attention now to what is happening to the iron filings. Hopefully this is coming through on the video. Try it a little closer here, but what you should see are those iron filings kind of lining up in patterns. Almost lines, if you will. Not straight lines, curved, but you should see patterns kind of like so. So what you're observing all the particles in the iron lining up along what are called magnetic field lines. Now that's kind of the super simple way to put it. I mean, really the iron filings are even becoming part of making the field lines in and of themselves, but the idea is that the magnet here has around it what we call magnetic field lines. And if you're not familiar with the idea of field lines, I've got videos and other people do on what field lines basically are. It's a way of representing and describing vector field type of phenomenon. It's very common to talk about gravitational field lines, electric field lines, also very common to talk about those. And in this case, we're going to talk about magnetic field lines. So you've seen now a little bit about what the field lines around around this horseshoe magnet look like. So I'm going to kind of back out and talk about, in a bit more general context here. So this picture on the left is a picture of what I would call a standard bar magnet. And bar magnets have both what's called a north pole and a south pole. And I will do this in another video, but if you mapped out the field lines around a bar magnet, they would look something like this. And some things to notice. Of course, the further away you get from the magnet, the weaker the magnetic field. And in the picture, that's demonstrated by the distance between the lines getting bigger and bigger and bigger. Again, you may want to go back and review vector field lines and kind of how to interpret them. A really important fact of life is that field lines around a magnet, they point from north to south, right? There's a direction associated with it. Now, we're going to get into a little bit more nitty-gritty detail here. So it's been experimentally determined that the magnetic force can be calculated using the following formula here. The magnetic force on a charged particle is equal to Q, the charge on the particle, times this product, V cross B, where the velocity is the velocity vector of the particle, and the B here is the magnetic field vector at any given point. This is an experimentally determined law. There's no deriving this. It is kind of, I guess I would call it the first principle in magnetism. Now, if you're not familiar with cross products, that's okay. This is going to be just a conceptual video, but going on a little further. So the QV cross B, magnitude-wise, can be written Q, the charge, times B, the velocity, times B, the magnetic field strength, times the sine of the angle between the V and the B. Now, again, if you don't have a background in trigonometry, not a problem. This is going to be a conceptual video here, but the magnetic field strength is defined around this equation, if you will. This is an experimentally determined equation. And if you solve it for B, and I put over here on the right, the magnitude of B, meaning the magnitude of your magnetic field, is equal to force over charge times velocity. Sine theta is dimensionless and therefore doesn't show up in that equation as far as that's concerned. Now, unit-wise, that means the magnetic field strength has units of Newton over Coulomb meter per second. And you can write that different ways. I'm going to just keep writing it like that. And like a lot of things in physics, the Newton over Coulomb meter per second has its own little pet name. It's called a Tesla. So magnetic field strength is measured in a quantity called a Tesla. And this is what a Tesla is. Basically, if you ran a charge through a magnetic field, and you somehow measure the force on it divided by charge times field strength, divided by the charge of the particle and the velocity of the particle, you would know the magnetic field strength at that region. Now, I wrote some important points here. This is important point number 1. This is how magnetic forces are calculated. And again, this is an experimentally determined set of rules here. I'm going to skip number 2 for a moment and go to number 3. It's a very important consequence of magnetic fields that you notice that it is velocity dependent. It is the only, of the very common forces of nature that you typically talk about in a college physics class, such as the gravitational force, the Coulomb force, and now the magnetic force. It is the only one of the 3 that's velocity dependent. So that's really important to notice. Magnetic fields only act on moving charges, and I underline moving because that's an important fact, and I'll go through some examples of that here in a minute. Going back to number 2, the direction of the magnetic force is given by what's called the right-hand rule, and I'm going to explain exactly what that means here in a few minutes with examples. For right here, right now, what that means is that the magnetic force is always perpendicular to both the velocity vector of the particle and the magnetic field it is in. So, very important facts about dealing with magnetic fields. Now, backing up, kind of in a bigger picture sense. So, we've got our picture of a bar magnet with the field lines around it. This field configuration is sometimes called the dipole field. I'll make another video about why that is. So if we were to pick a point, like maybe right here in our picture, right, 2 important things to know. The magnetic field vector at that point, the strength, or in a lot of my videos you'll see me talk about magnetic field intensity. What I mean by that is the magnetic field strength, or the magnitude of the magnetic field, is defined as force over charge velocity. I know that's a kind of strange sounding thing, but so it has units of Newton over Coulomb meter per second. And the direction of the magnetic field is defined as the direction that a compass points. So basically, if you take any compass, if you're just walking around and you look at the direction it points, it's telling you the magnetic field direction at whatever location that compass is. Now, most compasses are 2-dimensional in nature. Magnetism in general is a 3-dimensional concept, and magnetic field vectors, if you're in the northern hemisphere of the Earth, they actually point towards the north, the geographic north, and I'll talk more about that here in a little bit, but they typically point down into the ground as well, and I think I'll save that for another video that shows the kind of 3-dimensional behavior of magnetic fields. So this is how magnetic field directions are defined. And what that means is in our picture, if I put a compass right there, these field lines are telling us it would point that way. If I put our compass here, the picture is saying that the compass would point in this direction, meaning this is the magnetic field vector direction. If I put the compass, say, right here, the compass would point this way. That's how you kind of interpret these field lines. And again, if you go back and watch either my videos about field lines or others, whatever field vector you're dealing with, the direction is always tangent to your picture, to the field lines that describe it. Now, talk a little bit about right-hand rule. So the way you apply the right-hand rule in general is this. If I had 2 vectors, let me say A and B, I'm going to draw them like so, A, B, and you were to take A cross B, written out, you would write it like so. The direction of A cross B you get by using, again, your right-hand rule. You take your hand and you put your fingers in the direction of A, right directly parallel. And I mean parallel. Sometimes when I watch students and they're kind of, and I mention put your fingers parallel to A, and I see something like this or this or this. That's not parallel. Parallel means you should be able to use one of your fingers for a straight edge to draw that vector. Right? The next step in the cross product is you rotate your hand until you can sweep towards B. I call this sweeping. You might see other language with how other people teach how to apply this. Your thumb gives you the direction of the cross product. So the direction of A cross B in this picture is into the board. Now, I like to use unit vectors when I describe direction whenever I'm dealing with magnetism. Quick little review if you haven't seen mine or other people's videos on unit vectors. In what I call a ZATU, an X, Y, Z ATU coordinate system, just a standard looking type of coordinate system, plus I points to the right, minus I the left, plus J up, minus J down, plus K points at you, minus K away. I, J, K, again, are the three unit vectors we use to describe the directions within a three-dimensional coordinate system like this. So in getting back to this example, A cross B points into the board, or in terms of unit vectors, that would be in the minus K direction. B cross A would point at you, right at the camera here, out of the board, or in other words, in the plus Z direction. If we were to look at this example, if I had a charged particle right here, positively charged in the plane, and its velocity vector were this way, meaning this particle is moving in this direction, and we were to look at the magnetic force on it. Now, because of where it's at, the magnetic field points to the right. So applying the right-hand rule, fingers parallel to the first vector, V. Right, the magnetic field direction is this way. Rotate